Hi everyone, I'm ECK from FKE UTHM. So today in this video we are going to look at how to solve this question number 3, which is involving the voltage generated, the EMF voltage generated. Okay, so now look at question A. So you have a car travel at this speed. Okay, so this is the speed, this is the U. Okay, and if the Earth's magnetic field is this one, okay, so this is the B, this is the B. Okay, determine the induced voltage generated, okay, in the car bumper of length 1.6 meter, and assume that the Earth's magnetic field is normal to the car bumper. Okay, so we have to make some assumptions in these questions. Okay, the first assumption is the car bumper is made of conductor. Okay, made of conductors. So you just imagine this is the bumper. Okay, I just draw the bumper. Okay, made of conductor, and it is moving with speed. Okay, U. Right, and then okay, your magnetic field is normal. Okay, it's normal to your car bumper. So I would say that this is 90 degrees angle. Okay, so this is the direction of a magnetic field. Okay, so if you want to have a reference, maybe you can put this one. Okay, so this one showing some reference for the directions. Okay, so the B is Z directions, the U is Y directions. Okay, so now you have to find the voltage generated. Okay, so the voltage generated in this case is a motion EMF. Okay, because you have speed given, your conductor is moving. Okay, so you have these equations to calculate the motional EMF, right? Right, so the first thing, okay, come to the speed. Okay, the speed given, okay, is in unit kilometer per hour. Okay, kilometer per hour. So we have to change it, okay, to meter per second. Okay, we have to change it. So how to change this one? Okay, so we have to take this 120 multiply k. K is 10 power 3, right? Okay, and then per hour. Okay, this one is per hour, right? Sorry, this one is per hour. Okay, so you have to take this one to 60 times 60. Okay, so 1 hour you have 60 minutes, and 1 minute you have 60 seconds. So you have to do this. Okay, so you can calculate this one. So you have 120, okay, over 60 times 60. So it is 33.33 meter per second. Okay, meter per second. Okay, so now we can put it into the equations. Okay, so for motional EMF, okay, so integrate the U. The U is 33.33. Okay, so let's say the direction is Y direction. You put Y directions. And cross product with your magnetic flux density. Okay, it is 4.3 times -5. And behind you have a milli. Okay, so here it means that it will become 4.3 times 10 power -8. Okay, so because this is 5 and this is -3, so you have -8. Okay, and in the Z directions. Okay, in the Z directions. Right, and then DL. DL stands for the length of your car bumper. So if you refer to the coordinate system, your car bumper, okay, is referred to the axis X. Okay, in the X directions. And for the length, okay, length of the bumper, it is 1.6 meter. Okay, according to the questions. Okay, so now let's settle the directions. So YZ, you get X, right? So when the X dot product with the X, you will get 1. Okay, so this is how your vectors missing. So now it will become this, right? So yeah, okay, right here 1.6. So is 33.33 times 4.3 negative 8. Okay, so it is 1.43 times negative 6 here. Okay, so next we can do the integration, which we multiply it with 1.6, right? 1.6, huh? Okay, so the answer is equals to 2.29 times 10 power negative 6 volt. And now we look at question B. You have a conducting circular loop. Okay, so you can just imagine you have a circular loop. Okay, so of radius 20 cm. Okay, so it has a radius, right? Radius 20 cm lies in the z equals to 0 plane in a magnetic field. So this is the magnetic field. Okay, and you see here is a time varying variable, so that this is a time varying magnetic field. So you have to calculate the induced voltage. So in this case, nothing is moving, and the B is a time varying magnetic field. So you are going to generate transformer EMF. Okay, so what's the equation for transformer EMF? So for transformer EMF, okay, the equation is negative n, okay, showing how many loop, and then you have this time derivative, right, and B dot ds, right? Okay, so now in this case your n is equals to 1. Okay, equals to 1. Okay, now you need to integrate your magnetic flux density, okay, with respect to the surface of the loop. Okay, so if you draw your loop here, right? Okay, so this is a circular loop. Okay, this is your loop. Okay, so this is your loop. Okay, so you have Z, you have Y, and you have X. Remember what's the radius? The radius is 20 cm, so it's 0.2. Okay, 20 cm. Okay, so when we come to these integrations, right, so our B, we can put our B here. Okay, our B is 10 cos 377t, right? 377t, okay, in the Z direction, and dot product with the area of the loop. So in this case, we will use a cylindrical coordinate system. So it's r, dr, dphi, okay, and the surface is facing Z directions. So the r is from 0 to 0.2, right, and the phi is 0 to 2 pi. 0 to 2 pi. Okay, so this you can cancel out, right? So we can do the integration. So okay, so this part actually will remain, right? And then when we do the R integrations, okay, you can use calculator for the R integrations. The R integration, so you integrate x, okay, I mean it's 0.2, okay, from 0 to 0.2, okay, it is 0.02, okay, so this is the integration for the dr, and for the d phi it is 2 pi. Okay, so you can multiply them together, so then, okay, so it will become 2/5 pi cos 377t. Okay, so this is this part. Okay, so now we are going to do the differentiations. Okay, so for the differentiations means okay, we can straight away, so because the n is equals to 1, so we have this dt and 2/5 pi cos 377t. Okay, so you need to differentiate with respect to the t. Okay, so here I take out these 2/5 pi because constant, so cos will become sine. Okay, so at 377t, right? Okay, and then when you differentiate 377, so you have another 377 here. Okay, and cos to sine, and in fact you have a negative, right? So negative become positive. That's why this thing is missing. Okay, negative become positive. So I can multiply with 377. So now it become 473.75. Okay, and sine 377t. Okay, so this is the transformer EMF generated. Okay, as for this question C, okay, for this question C, and this question C is a question that we have tried in class in our PowerPoint. Okay, so I won't do it again, so you can refer to the steps that we have tried earlier on this question. It is exactly the same thing. Okay,